Hello, everybody, and welcome to our philosophy of maths sort of session. I was talking about the necessity of talking about math before we get into more advanced topics that has to do with science and all that stuff, simply because math is the building blocks, it's the logic behind it, it's the language that we use to express our whatever discovery or whatever knowledge we have. So let's delve deeper into this. Before I get into the questions, I would like to play a video. This video is from QI. This is like 15 years ago when Stephen Fry used to do it.
What does this prove? You may notice it's not written in usual mathematical language.
Yes, it's not a message from Al Qaeda.
No, it's not in Arabic. It's written in symbolic logic, if that's of any help to you.
Has it got something about the Portuguese coup starting in 75?
Not about that. Who was the great logician of the 20th century, the great British master of logic and mathematics? Sorry? Derek Trotter. He was also a great campaigner against nuclear weapons.
It's Bertrand Russell.
Bertrand Russell, Lord Russell. There he is, Bertie Russell.
He
Marvellous figure.
wasn't a barrel of laughs, was he?
They say that his breath was not good. I mean, that's in the biographies of Keynes and his contemporaries. He had very bad breath. But he was a remarkable man. And he wrote Principia Mathematica, which was a book determined to reinvent maths, because set theory produced all kinds of paradoxes which seemed to suggest that nothing could be proved or complete or consistent in mathematics, which was a huge shock. And so he had to set out to prove mathematics worked from the very first principle.
Very, very good at Sudoku.
He was, oddly enough, he was said not to be that good at mental arithmetic. But so in order to prove mathematics from the very beginning, you have to establish the first principle of arithmetic, and that piece of symbolic logic was proving that 1 + 1 = 2.
It's a bit late, the 20th century, to prove that, I'd say.
You're a bit late.
We've got quite a lot riding by the 20th century on 1 + 1 being 2, you know. Quite a lot of engineering happening, quite a complex international economy.
Oh,
If you find out that it doesn't equal 2, what do we do? Just burn everything. 'Cause God knows anything could fall on our heads. Money, you might as well eat it. Forget civilization.
Well, there is a general thought that if what were considered to be the sound foundations on which all mathematics rested were proved to be rocky, that it may mean that some of the ultimate answers of the universe will never be answered. But it's rather splendid to think you would give so much effort into proving
What an
1 + 1.
extraordinary achievement.
It
And
is.
You just have to bring up his halitosis.
I know, that was silly of me, but I love
You
that.
know, it
He was
comes
a great...
to something where you think you've achieved that.
Imagine meeting him at a party.
Old
though.
Stinky Russell.
I met this bloke at a party. He stank. And when I asked him what he did, he said he proved that 1 + 1 = 2.
What we were watching now was Stephen Fry talking about the famous proof of 2 + 2 = 4 by Bertrand Russell and Alfred North Whitehead. And the reason I'm playing this clip, I'm going to keep going back to it, because this is what we will be using to, stimulate our thinking of what mathematics is, essentially. What does it do? What is the subject of mathematics? What is 2 + 2 = 4 about anyway? You know, like, what is it? What is this object that when I say 2 + 2 = 4, what are we really talking about? Is there any meaning to these claims? And assuming that we can answer all these questions and assuming that everything else makes sense, then how do we know that they are true? So I'm assuming we've answered all these questions before. How do we know? How can we confirm that whatever we've discovered is the truth? So this is what we will be talking about. So these are the main questions about philosophy of mathematics, essentially. Okay. And the first answer to these questions is a traditional view called Platonism. And Platonism is a theory that, of course, Plato came up with, because he had this bigger idea about what things are, which is that existence, according to him, is this reflection of a higher sort of existence. So our world is a mere projection of a higher world where perfect things exist. And the main motivation behind this, if you can follow me on slide 4, there's the famous picture, of course, for King Charles now and his portrait. And for Plato, just like you can have many pictures of the same person, so the essence is the person, and then you can replicate that picture for like 1,000, 1 billion times. You can make a picture of that person, but then still you can preserve the essence. For him, there's absolutely no proof that there is no higher world, okay? And we are mere reflections of that higher world out there. Specifically and essentially because if you think of identity, so if you think of an apple, if you think of a pen, if you think of even a person, okay, you can take pictures of this apple that you can hold in your hand, but then the essence, the essential thing that you're copying from is the apple. But then you can see another apple and you say, oh, that's another apple, and that's another apple, that's another apple. Or if we were going to talk about more mathematical objects, oh, that's a square, that's another square, that's another square, that's a bigger square, that's a smaller square. So all these squares, nothing prevents them from being an image of the most perfect square out there. Just like our photos are images of us, and we are the essential, and we are the beginning, we are the actual source of that information. Nothing prevents our world from being also a reflection from this perfect world that he called the Platonic, or we now call it the Platonic world of forms. Essentially, if we think about mathematics, squares actually don't really exist in the real world. If you want to think of a square like a square, the lines don't have to have width, and the points cannot have length. And so the actual Euclidean square is invisible. All these squares that we are drawing are just mere representations, mere pictures of the conceptual square that we have in our minds. And where is that conceptual square? It comes from this world of forms, this world of perfect ideals, where you instantiate. That's the word philosophy. It's an instantiation. It's one instance. Okay, it's one example of a square. So this is the Platonic traditional view. What about salt crystals? I don't understand here. So that there's like perfect crystals, and I'm not really sure what you mean by this. But this is the main idea behind the Platonism. Okay. So when you call when someone identifies as a Platonist, they are talking about this kind of idea. Now, there are modifications. If you can follow me on slide 5 to this idea, before we discuss it, I'd like to mention. So it's not only about believing that there's a world out there. There's kind of a new revival of this Platonic view that people also now are finding more popular. On slide 5, you will find a picture of the proof that Mr. Fry was referring to. So this is the proof, or the short summary of the proof of something like 1 + 1 = 2. And it looks like absolute gibberish for most of us, for all mathematicians actually, unless you study the language, because we don't even use these symbols, some of them anymore. I can draw your attentions, if you follow me on Jitsi as well, to these symbols I'm marking in red right now. Can you see the marking in red? We have seen these symbols before. Do you remember? These symbols are familiar. I'm referring to the entailment symbol in the beginning. Okay, so there's this entailment symbol that begins the proof. Here's the equal sign. I'm marking it in red as well. And this is a belongs to sign, this small e behind the beta. So you have alpha, beta, and a small e. This means belongs to. I'm going to write it down. Belongs to. I'm pretty sure at least some of you are familiar with, are familiar with this concept. So we are on slide 5, and we are looking on Russell's proof of 1 + 1 = 2. And to be fair with you guys, I don't think that what this is a proof that 1 + 1 = 2. Especially if you read this English below, it says, from this proposition, it will follow when arithmetic addition has been defined that 1 + 1 = 2. what Russell is doing here is not really proving that 1 plus 1 equal 2. He's proving a version of doubling. Okay? I'm going to read it in English, the statement. We're not going to explain the proof, of course. I'm just going to read the statement of the theorem. I'm going to try to translate it to English. So he says, assume that you have two objects, alpha and beta, and he says belongs to 1. We're going to go back to that idea. What he really means is assume that alpha is 1 and beta is 1. Okay? The second line is assume that they are not the same. So their intersection is this anti-V is the empty set. Okay? The translation is assume that they are not the same, because of course, if you add 1 to itself, you will not get 2. So assume that you have 1 and another 1. Combine them. So this inverted cup here is kind of combining. When you combine alpha and beta, when you make the union of them, you create 2. And then you see this other symbol here, this small e next to the 2. Why am I making a big deal out of this e? Because the way Russell is defining number 1, implicitly here in his writing, is he is imagining a sort of class, a sort of collection in his mind. And this collection is called number 1. And the way he defines it is, I'm going to put inside it all the things that have oneness as a property. So you have 1 apple, put 1 apple in that box. You have 1 pen, put 1 pen in that box. You have $1, put $1 in that box, etc., etc. And when you make the collection of all things that are number 1, then you define oneness in that way. And why is this relevant to us in our discussion of Platonism? Because where is that property? What is that ideal? Okay, what does that really mean to have a collection of things that's called number? How do we know where to add them? We cannot access it. It's just by definition, those collection of things. And what is the common property that they have? It's number 1. Where does that property live? Out there in the world of forms. Implicitly, I'm not accusing Russell of anything. I'm just saying when you say belongs to 1, so now we can understand where he started. He says, just pick a 1 from that box and then pick another 1 from that box. Belonging to the box, that box lives out there in the world of forms. It's not anywhere here that we can touch. It's not anywhere we can access. We don't even know what's in that box. Just like we cannot access the perfect world of forms of Plato. Is this clear? Does anybody have a question? Am I losing you guys, or are we still, on board? I'm just going to explain. So we're going to have several answers for the problems of philosophy of math. I'm going to explain the theory, and then we're going to negate it, and explain the theory, and then negate it. So now I'm kind of preaching Platonism. So the mic is free. Please go ahead.
I'm reading in chat, salt crystals would be instantiations and not always perfect. I mean, I really don't want to be talking about salt crystals here. But yeah, they are instantiation of whatever we call salt crystals. So without going into the science of it, if you have this conception in your head of what a salt crystal is and how it's arranged, then that conception is somewhere in the world of forms. It's a conceptual thing. And every time you see an example of it, you're instantiating, or the actual thing you're seeing is an instantiation of that perfect form. So this is what it means. Another thing in chat is this a version of set theory? This is an old version. Yes. Some signs have changed, some signs have not. So I'm trying to, point out whatever we've seen before. But yes, this is a version of an elementary creation of set theory.
So I missed some audio because I was trying to. The Jitsu is not working for me. It worked.
It's fine. I think you can leave the Jitsi for now and just stay with us on Clubhouse.
Yes. So I mean, you were explaining the proof slide. So yeah, I got the idea. I missed some audio. So I don't know whether because I would like to understand the proof in a very simple way. So you've got the collection, you've got the box of ones, right? And then you have another box of ones. So you add that. I mean, how would did I miss anything or have you not worked it through? So how do you get a box of 2, right? Is it something like that?
So we haven't explained the proof, and again, this is not what I'm about here today. Because if I were to explain the proof, actually, I'm going to have to give you the entire history of because this is page God knows what 360 something. And so if you look at the statement, there's a reference to 54.26, 51.231, etc. So it's not a math class, and I don't intend to turn it into a math class. However, what I've explained is the statement of the theorem. And so the statement says, you take one and you take another one. So alpha belongs to this. So this is alpha. It belongs to this one. And then beta is another one that belongs to this big set of ones. Okay. And if you make sure that you're not picking the same thing, so alpha and beta, their intersection, I mean, here is the empty set. This anti-V is empty here, empty. If you make sure you're not essentially picking this common elements, or you're not picking the same one to simplify it, then you're going to get 2. This is the statement of the thing. I'm not proving it, but as a statement, this is what he's writing. And I'm only referring to this because just to highlight that even modern mathematicians, even mathematicians who claim to be, let's say, very material or very scientifically oriented and so on, are Platonic. And some of them at least are Platonic, because Platonicism gets this hard time between mathematicians and philosophers. It's kind of like, yeah, you're a Platonicist, boo, right? But actually, we can see here Bertrand Russell himself expressing, at least tacitly, that he is a Platonic, and he defines numbers in a sort of a Platonic way.
Yes, okay, good, thank you.
Wonderful. Sis Jane is asking, is mathematics an abstraction of reality then? Oh, we're gonna find out. Stay tuned. We're gonna tackle all of these. So there'll be 5 answers to our question of what is mathematics, and this is the first one. The first one says mathematics is just a mere reflection of a more perfect world we will call the world of forms. That is what we have for now. If there's nothing else, I will move to the next slide, which tackles the 2 main problems of this view. And I'm sure some of you are thinking this already. Number 1, we cannot access this world of forms. It's out there, okay, we believe you, Plato. You have this idea that there's a world of forms out there somewhere. Fine, perfect, thank you. But how do we verify that whatever is over there is here, or is at least reflected here or instantiated here, if we cannot see what is over there to begin with? How can we verify this coupling that you are establishing? And so this first question that we ask, where does math come from? It wasn't really answered. It's a nice theory, it's a nice hypothesis, it's a nice wet dream that Plato had. But, we can't really access it. Just like Russell did. He's like, oh, put all the things that have oneness in that set of number 1, and that's how you define it. How do I know exactly that they are one? Like, and I know that for us, in the real world, it's kind of banal. Oh, you grab a pen and it's a 1, and that, etc. Blah blah blah. But then, if you want to think about it from modern scientific perspective, something that has to do with quantum mechanics, etc., and so on. Can you really speak of, let's say, a particle like oneness like that? Does that particle move without interacting with other people? And if you want to, without particles, I mean, and if you want to define it in that way, then you're going to run into some problems. I'll leave it to John Mallinckrodt. Where is he, by the way? I'm going to leave it to him to dwell on this more and more. I'm just opening the door that this is an empty theory. It's not really answering the question. It's kind of diverging us, pushing the problem forward to another dimension that we cannot really access. It's not really answering the question. And it doesn't explain the question that Sis Jane is asking, which is, how do we explain that it really works in reality? Is this, okay, there's a world of forms out there, fine, perfect, very good. And it's reflecting on our world, fine, very good. But then when we do math in our world, it works. It's kind of reflecting something that has to do with science. It's useful, in philosophy and other things. So how is it that it works exactly? We still don't know. So the 2 main questions that we've asked in the beginning were not answered by Platonicism. And I kind of know, I'm cheating, but I kind of know that Jonathan is a Platonic sort of, has Platonic views. So I'm gonna leave the mic to you if you want to comment or argue for Platonicism against these two main problems.
Nope, not now. I'm listening and learning.
All right, cool. So at least I'm gonna keep referring you to other places where you can look. But essentially, if you really want to find out more, there's like 20 of these different answers. We call them 20 different, let's say, philosophies of math. You can find them in the Encyclopedia of Stanford. That's a good entry. You can find it on Wikipedia. Britannica has a good entry as well. I'm only summarizing here, but there's a lot to say. A lot of different versions of Platonism itself. Gödel, for example, the famous logician, was kind of a Platonic in a kind of slightly different way. But this is, if you ever hear the word Platonic or a Platonic philosophy or whatever, then this is the main meaning. All right. So if it's not a reflection of the world of forms, then what is it? And school number 2 on slide 7 answers intuition. It's called Intuitionism, and it proposes that mathematics, instead of coming from a world of forms, comes from the human mind intuitive processes. Okay, so there's the human mind, and that mind is coming with an already built-in intuition, an already built-in mechanism to understand, to make sense, to project onto the universe. And that thing that we are talking about is producing mathematics. Two very famous people who believe in that view are Descartes, the famous mathematician and logician. Well, I can't call him logician. Logic wasn't really born yet, but he was a philosopher and a mathematician. And Kant, in the critique of pure reason. I'm going to start with Descartes, the lesser-known example amongst people. Descartes, as you know, has uttered his famous sentence, cogito ergo sum, I think, therefore I am, in answering the kind of demon the dilemma. So he's imagining that, okay, if I'm a skeptic and I'm not sure of everything, how can I be sure that we exist? How can I be sure that the planet exists? How can I be sure that the sun exists, etc.? And what he comes up with is, okay, let me imagine that there is this evil demon that is always tricking me into believing that whenever I'm seeing something, it's not really the case, but this demon is tricking me into seeing it. So I'm looking and I see a tree, but then it's not really a tree. I'm being fooled. There's an airplane, there's a bird, probably not an airplane, it wasn't. But there's a bird, there's a fruit or whatever, then the demon is tricking me. Okay, then he continues to even doubt arithmetic and number. So this is a quote from his meditation. He says, arithmetic, geometry, and other disciplines of the same kind, which deal only with the very simplest and most general things, and then highlighted in yellow if you are on Jitsi, and care little whether they exist in nature or not. That's a different claim from Platonism now. For Plato, they do exist somewhere else. For Descartes, it doesn't matter. They contain something certain and indubitable. For whether I am working or sleeping, 2 plus 3 equals 5, and a square has no more than 4 sides. Nor does it seem possible that such obvious truths could be affected by any suspicion that they are false. Even when I'm not even sure of the exterior world, even when I'm pretty kind of feeling that I'm being fooled, even when I'm writing 2 plus 3 equals 5 and this demon is tricking me into believing that it is 6, in my delusion, I don't see how we can get more basic, he calls them. What is the exact word? Certain or more simple. It cannot be possible that such obvious truths, okay, can be affected by suspicion. It's obviously true, 100% that's 2 plus 3 equals 5. And why? Because he finds it, even in his delusion, his intuition, his inner dynamics is finding it that it makes sense. And if we want to understand more, there's a nice development with Kant. Of course, Kant has a whole other section here with his synthetic a priori, etc. We're not going to go in there. But he expresses this view and he says, space is the form of all outer intuition. So our spatial intuition, when we grab things, when we see things that are far away, smaller, and then closer, they are bigger, etc., that's kind of an outer intuition, he defines it. And inner intuition is the intuition of time. Kant is claiming that mathematics has started with us thinking and feeling time. And when we started counting to feel time, this basic intuition has helped us figure out the laws of arithmetic to begin with, and then all the other laws of math followed. And so if you kind of merge the two quotes together to form a kind of like a general view of what intuitionism is, these people, Kant and Descartes and others, they believe that we are born already with something that makes sense, and that something, one of its entailments, one of its, let's say, dynamics is mathematics. You can make sure that that something exists because our brains come up with mathematics. And you just cannot get out of it for Kant. How can you ever get out of your spatial and time intuition when you're using these things to start reasoning to begin with? You're using the time intuition that you have to come up with mathematics and come up with reason and come up with logic. You're going to use that to doubt it? There's no way. You are born with it. It's basic with you. It comes with the operation system. Okay? So modern intuitionists carry that idea, if you follow me on slide 8. And they have developed a system of mathematics, that has intuition as its base. So they refuse non-constructive proofs. A constructive proof is when I tell you, okay, show me how to do this. You show me 1, 2, 3, 4, 5. You show me the steps. Okay. So sometimes we cannot do that in math, or we'd rather not do that. We prove by contradiction. We say, okay, you want me to prove that A is the case? I'm going to prove that negation of A is impossible. You want me to prove that pi is an irrational number? Well, I cannot do it directly, but what I can do is assume it's irrational. I can generate a contradiction, which means that pi has to be an irrational number. Okay? Now, this they refuse because this is not in the intuition. And it might seem a little bit odd for my listeners, that's because we feel that we kind of have that intuition. Either things are true or false. But these people, the intuitionists, they don't even accept the excluded middle rule. They also made this new logic that they have. I linked it. I'm not going to talk about it. Brouwer and Heiting are famous figures there. They are very modern. They made their own analysis. They made their own algebra. Heiting algebra is a very interesting algebra. We spoke about something like this in let's say 3 or 4 months ago when we did the logic thing. I was asked whether you can use logic to talk about Boolean logic to talk about things that are neither true nor false. So things that are kind of mixed, we're not really sure, etc. And Heiting algebra, you can actually do that. So starting from true and false, so 0 or 1, you can kind of generate a very interesting. All of this is based on this idea of intuitionism. Some people even from the school, they reject infinities. Why? Because infinity is not something in our intuition. It's not something that we can grasp. It's not something that we can even understand or make sense of. So the extreme people in this school have went towards finitism, we call it. So mathematics without infinities. And you can make actually calculus, well, you can call it calculus, it's a different thing, without invoking infinities or infinitesimals. So this is the school of intuitionism, and I'm going to leave the mic free to discuss and answer your questions. The ontological status of real numbers is also rejected. Yes, absolutely, Wissam.
I might be jumping the gun after I've looked ahead in the presentation a little bit, but it seems this intuitionism, at least from these pre-21st century philosophers, is very much anthropocentric, and it ignores the fact that we now know from studies in animal behavior that, let me turn my engine and heater off. We now know from studies in animal behavior that other species have act out forms of mathematics as manifested in counting, or even in the case of amoeba solving mazes, doing computation, which, insofar as we understand computation, is based upon logic and formal mathematics. I don't know if that line of reasoning is acceptable in this
I'm not sure. I was able to follow. Can you kind of rephrase it?
Sure. So Descartes and Kant and these other philosophers that you're referencing are thinking purely in forms of human beings' interactions with mathematics, our species. But we now know that there are species that existed before humans that now exist that perform counting processes.
You're referring to that animal kind of instinct of doing math.
Well, not instinct. Well, observable procedural activities that are correspondent with human relationships with mathematics. So this goes all the way back to amoeba, even, which have been around for hundreds of millions of years. So that seems to be, it seems to take it out of intuitionism being a purely human construct and something that has been independently discovered by other species. So when a dog is catching a frisbee, its activities and its anticipation of the path of the frisbee correspond to our formal descriptions of the frisbee's path with calculus. But the dog isn't doing calculus, but it's acting in correspondence to the existence of a calculus interpretation.
Even when you're catching the frisbee, you're not doing calculus. Even the most advanced physicists amongst us, they don't do calculus when they are catching a ball or a frisbee. So I'm not sure if I have read this argument with an intuitionist before, but I kind of see here where you're kind of driving. So it kind of reinforces this idea that, well, since we can do it to begin with, then this knowledge has to be tacit in our nervous system somewhere, that we can, just like animals, catch a frisbee. And now that we are discovering the rules of mechanics and the rules of how things move, etc., and so on, now we're just formalizing it and writing it down, but it has always been inside us. Is this what you're driving towards?
I'm not sure. I'm still thinking.
I'm not sure either. I'm thinking with you.
Now, Wissam seems to have some objections here in the written chat.
Let me take a look. He says it's irrelevant even if they are better at math than we are. Absolutely, yes. Yes, I agree. Because if we were to, discover a new alien civilization, and they are better than us at math, we still have the same problem to explain our math. Yes, I agree, absolutely.
Mm-hmm. Fair enough.
So we first have the Platonic school, which tried to answer the question, where does math come from, what is it, and how do we know it works? We couldn't really get an answer. And now, if you follow me on slide 9, we will discover also other problems with intuitionism. Number 1, we cannot access that intuition. Same problem with the Platonic view. This intuition that people posit that exists, again, we understand why they do it, but we cannot really access it to verify that our intuition is generating the math. The theory is there's an intuition somewhere inside us, and this is causing the math to come out. Okay, how do I know that? I don't even know what intuition really means here. I can't even be sure that all humans share the same common intuition to begin with. How do we know that? We know that we behave in similar ways, but how do I know that there's the same intuition with every? I'm pretty sure that we can disprove this, actually. Okay, like 8 billion people, 100 billion people across all history. People have born 10,000 years before we are born have the same exact intuition we have. That's kind of unlikely. Intuition changes with culture, it changes over time. I'm using this word, and I don't even know if there's a well-defined definition, a well-formed definition of this word, intuition. I'm not really sure what they mean, but whatever it is that they mean, I'm trying to kind of question the very concept. Okay. Point number 2 is that even if we just accept that intuition is behind all of this, it doesn't really explain how do we know that math works. So our intuition is telling us that this math makes sense. Okay, can we confirm? Can we deny? Is this so? Our intuition tells us all sorts of things. Should we believe our intuition all the time? If you're on an airplane and then the pilot said, "I have never had training in flying planes. I'm just gonna fly it by intuition," would you believe? Would you like? Yeah, sure, I'm fine. heart surgeon doing heart surgery operating. It's like, yeah, I've never had training. I'm just going to follow intuition here. Is that reasonable? You're going to get out of there. You're going to run out of there as fast as possible. And I don't know if we cannot trust intuition there. Why would we trust intuition while we're doing mathematics? Plus, the biggest problem of them all is that if I go back to slide 7 and I read Kant again, Kant proposes that our intuitions behind mathematics, so he kind of splits mathematics in his mind between arithmetic and geometry. Geometry comes from our intuition of space, and arithmetic comes from our intuition of time. Well, going back to slide 9, we live in the 21st century. We have discovered special and general relativity. Both these theories combined, they negate, they destroy this idea that Euclidean space is the space that we all live in. It's the same for everybody. No, space bends and it contracts and it interacts with energy and matter and all that stuff. And time is not common between all of us. Time differs between us, each one with their own frame of reference and their own clock. So this intuition that Kant was talking about, it's not true. We know it's not true now. At least it could have come from somewhere else, not time and space though. Time and space, if our intuition were to align with the physics, should have generated different mathematics for each and every individual amongst us. We all share the same mathematics, we just don't share the same space and time. So whatever Kant had in mind is absolutely not the case. So these are the main 3 problems. Again, you can totally find more if you dig into the articles, but these are the 3 main problems of intuitionism. Yes, dude, cool.
It may distort what Kant says a little bit, depending on the movement of the observer. But if all humans are somewhat moving the same speed, then it doesn't really matter when it comes to simultaneity.
Okay, I will accept. How about our intuition with objects and how objects move? There are very fast objects in the universe, and can we use our intuition to verify that? So let's say the problem of muons coming from the sun, and we know from our labs that these things should not survive the trip, but then they do because of relativistic effects. How can you justify that based on intuition? What part of your intuition accepts that time will dilate to that point? You know what I mean?
That's a valid point, but with Kant, he's more concerned about reason, like the reasoning of the observer, which would be all of us in this room, and our ability to reason, and that because none of us are really moving as an observer at a really high speed, we are still observing simultaneously what is happening.
I'm not sure if I follow you. Let me ask you before I try to answer. Are you positing that our intuition of time, just like Kant does, kind of helps us to develop arithmetic? And when we develop the rules of arithmetic and numbers and etc., and then this allows us to reason about the universe and discover something like special and general relativity. Is this what you're trying to say? So even us now today, when we learn about all these things, we still rely on this basic intuition of time.
Yeah, I put a YouTube video here about basically what I'm talking about. It's the relativity of simultaneity, and with us at the speed we are moving as observers, we are still experiencing everything simultaneously as it is happening, unless somebody's moving at an incredibly fast speed, then they would experience time and space differently. But with our feet on the ground, it doesn't make as much of a difference for an observer as it would with what you were talking about with objects outside of oneself.
It wouldn't. I absolutely agree with you. But again, I will ask you the question. If I'm relying on my intuition, and my intuition says we all here share the same time. I'm speaking to you now, and you can hear me now, and it's, I don't know, it's dark now, so it must be, if you live in the same country or the same region, dark as well. And then when the sun rises for everybody, and so on and so forth, okay? I'm relying on that intuition. And then someone tells me there's a particle that's supposed to be dead 2 weeks ago, and it's not yet because it's moving very fast. That piece of knowledge is against my intuition. If I am relying on my intuition to figure out things about the world and to encode things about the world in mathematics, that intuition in that particular instance fails me completely. That piece of knowledge that is relativity is completely opposed to my intuition, absolutely in contradiction. And again, even if, like, you know, don't forget points 1 and 2, okay? So even when, you know, I want to accept with you, okay? We use that intuition, and then we develop, and then we grow out of it. Fine. How does that explain how math works? Why does it have a relationship with the universe? Because we are born from this universe, so we are a random collection of atoms in this universe. We just happen to have some intuition in our brains, and that intuition somehow aligns itself with the dynamics of the universe, and it's able to tell us what happens. I don't see that as a valid explanation.
Yes, I do not agree with you. Still, the point remains that with Kant, he is very much centered on reason, and the general relativity aspect probably would not dilute his philosophical stance upon that.
So Kant has this strange view. I call it strange. I mean, it has made sense for at least 200 years. He calls something the synthetic and the analytic. And then he has a priori and a posteriori. And then he calls mathematics a synthetic a priori. Very quickly, synthetic analytic. Synthetic means this is a piece of knowledge. This is a sentence. It's a claim that adds. It moves forward. Okay, so you gain a new information. Analytic, it's something built in. You're not gaining new information. The classic example is bachelors are unmarried. Like, I don't need to, you know, do any investigation. I don't need to, you know, make sure of any. It's just matter of definition. It doesn't add anything new. Whereas a synthetic claim can say, for example, bachelors are unmarried. Bachelors are unhappy. So if when I say bachelors are unhappy, what I'm saying is, oh, I have to go out now and check. This is not in the definition of a bachelor to be unhappy. A priori, a posteriori is very similar with a slight distinction. A priori means before experiment, and then a posteriori means after experiment. So I need to access knowledge to know that bachelors are unmarried, for example. I don't need to go ask bachelors, are you unmarried? Are you unmarried? Are you unmarried? No, I just know that a priori, before doing an experiment, before checking. A posteriori means I'm going to check after. I have to go to the world and then collect data. I have to go do my search. Now, whether will Kant change his view or not, I'm not sure. But Kant claims, based on those two views, and I'm really sorry I'm brushing over it because it's kind of technical, and I don't want to bother, you know, I don't want to overload you with jargon. But what he claims is that mathematics is this very particular piece of knowledge that is synthetic but a priori. It is already built in the definition, and the definition comes from intuition, remind you. But it is synthetic. It tells us something new. I'm not sure how you marry this with our modern discoveries. If it is based on definitions with intuition and it tells us something new, he claims that space and time, that Euclidean sort of unit is the. We don't even have Euclidean space. Forget about time. The planet we live on is a sphere, and we're using spherical geometry to travel on it. Of course, Kant knows it's a sphere, but he did not know that the shortest path on that sphere is not, quote unquote, a Euclidean straight line. It's another kind of straight line. He had no idea. And then, of course, in the vast universe, there are other developments happening. So again, we have to ask Kant if he would change his view or not. I'm not sure. I think these developments at least bend his theories quite a bit. Wissam in chat agrees with you, by the way. He thinks that Kant would not change his mind. Maybe.
Regardless, you're doing a really great job.
Thank you very much. We're gonna keep going. We're gonna discuss the theory, preach it, and then poke holes in it. Thank you very much. In chat, Dam Shumais is asking, interesting question. The title: have the implications of your answer for epistemology been discussed? No, not yet. We're just counting the theories. We're just enumerating the multitude of answers and how they reflect on, and we're just, kind of balancing them, the for and the against. Maybe later on in the discussion, we can probably tackle that a little bit. Anything else on intuitionism? Any intuitionists amongst you who would like to raise a point we haven't? Yes, sir. Welcome to the stage.
Hello, Logic.
Hello.
I don't have a point to raise, but I do consider myself an intuitionist.
Okay.
I don't have a point to raise only because I haven't. I've only been in the space for about a couple minutes, so I wouldn't. I'd rather catch up.
Oh yeah, absolutely.
Was intuitionism discussed?
Yes, we just finished discussing it. So just cool. do me a quick. Let me actually copy paste the link one more time. So there's a link in chat for the slides that we have.
Oh, perfect.
And if you want to just click on the top of the room as well, some people were able to join, some people weren't. I'm not really sure. Depends on the device. Today, I'm having technical problems for some reason. So either you click on the Jitsi in the top, or you click on the link in the chat. Just take a quick look on the slides, and then later on, if you want to go back to it, you're more than welcome. Okay, the points are nicely summarized there. So, and if you are an intuitionist, you can get the main idea. Okay. So number 3. So if it's not from intuition and it's not from the world of forms, where does it come from? The answer number 3 is from the physical reality. From our experience, from the human mind's experience in the physical world. Whenever a pile of 2 objects is pushed together with a pile of 3 objects, the result is a pile of 5 objects. 2 apples, 3 apples, 5 apples, 2 pens, 3 pens, 5 pens, 2 plus 3 makes 5. This view was developed, of course, in the same period by other mathematicians / philosophers. One famous name here is John Stuart Mill. Of course, he was the main proponent of this kind of view. And to be fair, this is a very common view as well, and it has many different attractions. I'm going to just name a few examples. There, you can find quite a lot. I have a few examples in the slides I'm going to name. A full moon gives you the impression or the let's say the inspiration to create a circle. A tree trunk will give you the inspiration for a cylinder. The straight line that stretches to infinity comes from the horizon. So you look at the horizon and you get that inspiration. The plane, the Euclidean plane, that infinitely thin and infinite extending surface comes from the surface of a lake. Okay, and so on and so forth. It's all these objects in nature give us the impression, give us the inspiration to create the perfect images of them. So it's kind of opposite of Platonism. Platonism, the perfection is up there somewhere and then it goes down to us. And this kind of view is kind of more Aristotelian. We look at the objects in the world and we kind of generate the perfection from them. Okay. The word calculus, if you know, comes from the Latin word and it means pebble. And calcul in French means the same exact thing to this day. It's just a pebble. And the reason why we have that is because people used to use pebbles for counting. So again, math comes from the natural world. It's come from the real world. They used to put pebbles or small, let's say, wooden thingies on abacuses. Abaci, I'm not sure what the plural is. They used to do vote counting using these small pebbles. And let's say, as well, we know this, shepherds, I'm looking for the word. Shepherds, when they used to take their sheep to the grazing grounds, let's say, and then they bring them back, they used to have a small bag, and then for every sheep that leaves in the morning, they put 1 stone in the bag. and then they remove that stone whenever the sheep comes back. And then when you end up with an empty bag at the end of the day, you know that you have all the sheep. So this is kind of a basic intuition of how to count, creating this one-to-one pairing between the objects in the world and the other objects. So one sheep, one stone, one sheep, one stone, etc. Also in the ancient Egypt, let's call them the pharaohs or the pharaonic civilization, there was a job which continued until modern times, and then when we had modern equipment, it's kind of disappeared. There was a job called the stepper or steppers, quote unquote, and these steppers were people who are trained to make steps in very monotonic ways, and those steppers would be land surveyors in ancient Egypt. Whenever the Nile floods, it kind of erases all the landmarks between farmers and their lands, etc. And so what they would do is they would pace, again, the pacers, they would pace the land and mark it again one more time. Again, relying on natural kind of bonding with the physical world, etc. Arithmetic with negative numbers and zero was a very late discovery in history. If you go back to European mathematics, 15th, 16th century, you will read those manuscripts and you will find people take great lengths. They go to great lengths just to avoid writing a minus sign, just to avoid saying minus, just to avoid writing zero. Because in their mind, I'm relying on nature. And in nature, the least number of things you can have is one. What do you mean zero? A symbol that is something for nothing? And again, here, you have to go back to, medieval kind of mentality. If there is a symbol for nothingness, but God is everywhere. So for the church in Europe, that was blasphemy. Now, in contrast, in China, zero as, the symbol for nothingness or the empty set has been existing for quite a while, let's say since the 2nd century BC. But also it has risen, they say, historians say, but it's kind of believable to postulate that it has risen from trade necessities and calculation necessities that have to do with debt. So they started using negative numbers and zero to express that kind of relationship. So it's again something from the real world that we have kind of generalized or taken inspiration from. Probability theory, famously, Girolamo Cardano has written his book, which, by the way, does not have the negative numbers or the zero. So you can take a look at that Latin manuscript. And he wrote the probability from gambling. If we didn't have gambling games, we would not have come up with probability theory. Even aliens. We don't know that they exist. But if you follow me to slide 12, we're going to watch a video about the disk that we have put on Voyager 1 and Voyager 2. Carl Sagan has engineered this disk to try to communicate with aliens. Now, we're going to look at this video. So if you're not on the Jitsi, you can go in now. I'm going to count till 3, let's say, very slowly. And we're going to play. Again, it's a 1-minute video. For people on Clubhouse, I'm going to try to route the audio one more time. And we will discuss afterwards. So 3, 2, 1.
Aliens probably wouldn't know what to do with a phonographed record. NASA had to provide a set of instructions on the record cover. But what could they say? How do you begin to communicate with a life form that evolved entirely separately from us? Scientists at NASA had to invent a code that anyone living in the universe might be able to decipher. So to do this, they started with what is by far the most commonly found molecule in the universe: hydrogen. This diagram illustrates the transition between the two lowest states of hydrogen. Any spacefaring civilization will probably understand the properties of hydrogen enough to know that when this transition happens, radiation is released, with a definite wave period. In human terms, we say this period is about 0.7 nanoseconds. This wave period is used as the basic unit of measurement for the rest of the diagrams on the cover. These are the instructions on how to make the record work. Assuming aliens wouldn't have record players like we do, NASA included one on the craft, with the needle already in place. These markings are binary code that define the speed you'd need to turn the record to get it to play correctly. Translated, we get over 5.1 billion hydrogen transition wave periods, or about 3.6 seconds per rotation. At this speed, you would begin to hear greetings in 55 different languages.
Hello from the children of planet Earth.
This would be followed by music and sounds from Earth, like a train in motion, crickets chirping, fire crackling, laughter, and a baby crying. This section explains how images can be pieced together from recorded signals. A replica of the first image on the recording is shown here, so the viewer can verify they decoded the signals correctly.
Very quickly, this was a video about the Voyager 1 and 2 disk. That disk we have sent to space to communicate with the aliens. And the video was explaining some of the notation on the disk. And if you follow me with slide 13, there are also some pictures on that disk as well. There's kind of 40 pictures that detail human life, etc., etc. Someone drinking water, someone holding a baby, etc. Amongst these pictures, you will find these ones that I have put on slide 13. And these pictures have numbers on them. To explain to the aliens, if you've seen in the video, we're relying on this basic understanding that there is a hydrogen atom. Whatever they have, they must have seen a hydrogen atom if they are sophisticated enough. So we have used that fluctuation of the hydrogen molecule between the two energy states. We have used that as our unit of time. And then we have used that to define numbers. And then from that, they just start using regular numbers. They start writing on that disk that the aliens will see. They start writing our numbers, the number system that we use today, and define our units. So you will see, for example, 1,000 grams is 1 kilogram, etc. And in the picture below, so between the other two on the top, you will see like our location relative to the other galaxies and stars. So you will see there's a picture of Andromeda, which is our nearest neighbor galaxy. And the small dot on the top is kind of planet Earth. And if you zoom in, and I will try to zoom in here, you will see that they have mentioned our location in the center as a planet using these dots and kind of ticks. And these refer to our positions from supposedly known pulsars. So a pulsar is a star that pulsates at regular intervals. And if there's an intelligent alien civilization, they will know where to find us because we have located ourselves relative to some of these stars. And again, we are using here ticks and dashes and whatever. And if you're wondering how would the aliens know, well, it's explained on the other picture. What is a dash? What is a stick? Whatever. And we use 1 dot to denote 1, 2 dots to denote 2, 3 dots to denote 3, and so on and so forth. So if you want to drive down realism, right, that's it. We're not even, we're so sure that it comes from the real world that we have used this method to define numbers for another civilization. Okay? So here is the position of Intuitionism. I will leave the mic for you guys to discuss. Sorry, I said intuition. I mean physical realism now. This is the third view, realism. And this is the case. And I believe we've made the case for realism. Are there any realists in chat? Are there any realists in the room? Let's discuss it a little bit before we come up with the negation of it or the rebuttal. All right. I have to answer Adam Shumaiz in chat. He is, or she, I think it's a he, you spoke with us. You're putting a link in chat about the earliest zero. I'm not sure if this is what I think it is. There is a distinction between zero and two separate functions. There is a function of zero as a placeholder, so 10 and 100 and 1,000. And I kind of glanced the article, I didn't read it, but I think this is what it's talking about. So this is an example of the zero that is a placeholder, 10, 100, 1,000, 10,000, etc. And there's another function for zero, which is a symbol for nothingness or a symbol for the empty set. And I'm talking specifically about that idea of nothingness it's a much more modern idea than it is, and negative numbers as well. Because the argument for this is, from a realism point of view, is that you cannot find anywhere in nature. So these developments could not have. This proves that we have come up with mathematics based on our reflection about the real world. This is what realists make of it. I have to read the article. I'm not sure if he's still in the room actually, but I have to read the article again and make sure this is what it's talking about. But I think this is the case. So, if no other business about physical realism, we're going to move to the rebuttal on slide 14. And this view has, like other views, many problems. Problem number one is we started with 1 apple plus 1 apple make 2 apples, and 2 objects plus 3 objects make 5 objects, and then we generate arithmetic. Well, question, what does 1 trillion apples plus 1 trillion apples make? The answer is, if you want to go follow the real world, apple juice. If you really want to follow the real world, actually we don't know, because nobody has put 1 trillion apples plus another trillion apples and counted. Nobody's ever done that. I'm not even sure if 1 trillion apples exist on the planet. I'm not even sure if you put 1 trillion apples and another trillion apples, you would get apple juice. You probably would get a black hole if you concentrate that mass somewhere very tiny. I'm not sure. I don't know. So maybe our real intuitions has helped us with 1 plus 1 equal 2, but a trillion plus a trillion, that came from somewhere else. A gogol plus a gogol, definitely not from the real world. A gogol is 10 to the 100, so that's 10 with 100, 1 with 100 zeros next to it. And the number of atoms in the universe is not enough to make this number. This number is way too big, even for the atoms of the entire universe. I'm not talking about the atoms of your body or of the planet Earth or the solar system or the galaxy. I'm talking about all the atoms in the universe. This number that we have created is way bigger by huge factors than the number of atoms in the universe. How are we dealing with it? Why are we dealing with it? This is not in the real world. There are no straight lines in the real world. There are no infinities. There are no dimensional points. You can claim that we looked at a line or at the horizon and located the line, but that's just your own belief, your own what? How do we know? Someone else can look at the horizon and say, well, this is just the horizon. And if you want to look at the real world horizon, it's not really straight. It's kind of bent a tiny bit. So getting inspiration, this inspiration is not coming from the real world. It must have come from somewhere else. The warehouse of mathematical theories, all those mathematical theories we have that we have accomplished, that we've packed all over the years, across civilization, across time. These things, they most of them don't even have applications in the real world. Forget about their origins and their topology and then J-tuples and those infinite vectors with the the density of this is just we don't even know where to apply these things. We're just doing it for the sake of mathematics. I'm not claiming that mathematics. I'm just saying it's whatever the purpose is. It's not the real world. These things they cannot have application. Infinities of infinities of infinities, that doesn't have any application in the real world. You cannot even get there from the real world. There's no reason why you would. For the most part, we still don't know where mathematics came from, if that is the case. So I would give you that some of the mathematics, the 2 plus 3 thing, whatever it came from, it's okay, I accept. But then most of that mathematical warehouse, we still have no idea where it came from. So even if we accept this as an answer, it's a very partial, minute, small answer. Neither did we explain how do we know that mathematics works and why. Okay, mathematics is our impression of the real world, our generalization from the real world, our reflection on the real world, whatever. Why does it work so well? How does it work so well? What guarantees this? Absolute silence. This is the third view that we're talking about. Number one, Platonism, not really working. A world of forms projecting on our world. Yeah, we don't know that. No, that's not cutting it. Number two, we had intuitionism somewhere in our intuitions, in our own brains. No, it's not cutting it. And now the real world answer. And the real world is not cutting it. Three different answers of why mathematics work and where does it come from. And for the most part, even, there's some nice examples that we can find here and there. For the most part, that mathematics that we are talking about was not properly explained. The sources of explanation are three: some other universe, ourselves, this universe. These are the three answers that we have thought of so far. None of those cut it. I'm going to pause here. I'm going to ask you, without cheating, is there any other source that you can think of for the meaning and for the truth and for the explanation of the origin and ontology of mathematics? Neither this world, nor another world, nor our own brains are explaining it so far.
Okay, I'm not sure that I'm really fully grokking this, so this may be really stupid, but I think that what I was getting at before, in terms of mathematics being, how shall I say, a manifestation or a demonstration of interactions of ourselves with the real world. It was sort of a more interactionist perspective, that when the dog is catching a frisbee, it's acting in accordance with things that are perfectly described in calculus, for example.
Okay, so the view you were kind of expressing falls not only under intuitionism, but a little bit more leaning towards this idea of physical realism, right?
I think so.
Okay.
I'm grasping and struggling here, so.
All right. Yeah. This is perfect. This is very good. So, again, we have to think of the whole warehouse of mathematical theories, this whole collection of mathematical theories. If, let's say, somewhere in our nervous system, we know and we can observe, and this is very much measurable, that either us as human beings or other animals can, and probably animals are better than us at this actually, with all our calculus and all our math and all that stuff. Animals are much quicker, they have much quicker reaction. Even a fruit fly has a way quicker reaction than you have. And so these things, this knowledge of how to act in the world is kind of embedded in their nervous system, at least tacitly. How exactly? We have Wissam here, neuroscientist. We can go to his room, and probably he can come up now. I'd love to hear his voice here, and we can dwell on how exactly is this kind of encoded in our sort of brains, in our nervous systems. But if we can find an example for that, how can we find an example for a vector that has not only infinitely many dimensions, but those dimensions are an order of infinity that is dense? Okay, so it's a dense infinity. So it's like the real numbers. It's not like the first, the second, the third, the fourth. It's kind of 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 2. I don't even know where to place two numbers between. If you start with 0 and you ask what's the next one, you can never find it. So we call this uncountable infinity. Okay, I'm getting a little bit technical here, but these things exist not in a very sophisticated math. These things exist in high school math. So that mathematics, we are using that mathematics to do calculus, and that mathematics is used to explain the real world. Not the mathematics that we do the one object plus one object equal two objects. We're using that complicated mathematics that does brings infinities and infinitesimals and all that stuff to try to describe the world very shyly. Scientists always refer to their work. We're just modeling. It's a nice thing that we created that kind of predicts what will happen up to a certain error. So if it was really the real world that was our influence or our inspiration, we would have found somewhere a shortcut than to invoke some objects that are never going to be part of the real world, never going to be part of our computational theory, never going to be part even to fit on anything, these infinities. You know what I mean?
But those are within mathematics extrapolations of the mathematical system. whether or not we've experienced them. Is that correct?
Not sure. I'm not really convinced that getting to those kind of complicated ideas is an extrapolation of things that we already seen. Again, well, how would you get the idea of an infinite vector that has infinitely many, like you have seen what exactly to go there? I'm not really sure. You can always claim that, and it's a theory out there. I'm just questioning the validity of this conclusion. How do we really know that every mathematical object we have can be traced back to some real world, let's say, metaphor or some real world inspiration?
Doesn't that arise out of the process by which mathematical proofs are built? That mathematical proofs are built on what is previously been proven and then extrapolated. So infinity, for example, we cannot individually perceive or experience infinity, but infinity comes by virtue of having a set of numbers and knowing that you can always have a number that is larger than the number that has been enumerated.
So just because we're having a larger number than the number we've just enumerated, we just claim that those infinities come from the real world?
Aha!
I see in the real world, yeah. So in the real world, all you need is a trillion. It's more than enough for you to do whatever application it is that you have in the real world. And even if you want to posit that the idea of infinity is coming from, let's say, looking at the sea and saying, oh, every single drop in the sea is now a lot. If you're going to count these, or the grains of sand, right? I'm going to count the grains of sand, and it just never ends. And we kind of created that idea of infinity. I might believe you, okay? But then why do we need to take that trip of going there, extrapolating those ideas that don't exist in the physical world, and then coming back to the physical world and saying, not the ideas that were examples of the physical world, but other ideas, those ideas that we've extrapolated, are the real explanation or the more accurate explanation of the physical world. If the physical world is the source, and if the physical world is the inspiration, it could have found a shorter way. Every time I look at a mathematical model, we see these objects that are not found anywhere. And if it's not found anywhere in the real world, I'm only believing your word that says, oh, we've just created those out of some inspiration. Probably what's really happening is we have these objects in our theory, and now as you and I sit down on this table, we are thinking of where can this come from? Where could have this come from? Infinity could have come from the sea. Oh, infinity could have come from space. Oh, infinity could have come from the grains of sand. Who knows? And even if we know, does that explain? Okay, I will give it to you that it's does that explain how mathematics kind of couples with the real world so nicely? Does it explain how we know it really works and we can guarantee that it makes sense? I'm not sure. If we ourselves are looking at this external world and we're kind of building inspiration, it sounds more like poetry than actual serious math to me, doesn't it? So there's a big question mark for me there. Hero is asking, is it because we have discarded all the math that does not work? I'm not sure what do you mean by work. If you're thinking of the physical world, which is the context of this philosophical view, then I don't agree. In fact, again, we have adopted the mathematical theories that cannot be known whether they work or not in the physical world. Ideas of infinities, calculus, infinitesimals, all these ideas should not have applications in the real world, yet they are the best tools. So throwing away those tools should come first if our reference is the real world. We don't. We keep them. We like them. They apply better to the real world. Not sure if I answered the question here, but I think this is where you were shooting. Yes, go ahead, sir.
Well, those each were sort of separate responses to things that were being said. The first thing I wrote was just my response. You challenged the audience. You challenged us to come up with another answer, and I just conjectured one. So what I said was
sorry, another answer to explain how mathematics works. So another theory, or an answer to how realism works?
Well, you tell me what your question was, because maybe I misheard it.
I asked both. That's why I'm asking you.
Okay, you asked both of what?
Just go ahead.
I think this is probably then my just initial speculative response to both of those questions that you uttered at the same time. So, the interaction of the interface of intelligence, not interfaces, but the interface of intelligence with appearances.
The interface of intelligence with appearances, you say?
Right.
Yeah.
So
What do you mean, really?
the analogy is like hardware and software. The interaction between uh, the mathematical language of software expressing itself through the hardware creates a feedback loop which produces new forms of possibility that can then be subject to the interactions that are possible to take place. So really, it's not meant to be a complicated answer. It's meant to be like, well, maybe all three of these ideas are pointing to a whole, and they're pointing to the same whole. And that would be that it doesn't have to be mathematics doesn't have to come from the brain or the ocean or the blah 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 it can come from the interface of awareness or intelligence with what it is producing, expressing, regurgitating, and so forth.
Okay, so to use your analogy,
yes,
I think this is easier to reiterate what the real question here is. You're saying that mathematics is produced between it and the human brain as an interaction.
I didn't say
so we interact
I
with
didn't say the human brain. I'm just clarifying.
Okay. So what is it that when you say hardware, what do you really mean? I assumed it's the human brain. What do you mean hardware?
All of what you're calling physical reality is hardware.
All of what I'm calling physical reality is hardware,
Yes.
and then what is the software exactly?
Intelligence.
Is it not part of the physical reality? Oh, okay. So you're kind of like you're splitting intelligence.
No,
from
I'm
anything.
I'm pointing out two aspects that are always connected and can't be separated.
Okay, but then when you say everything in the physical world is the hardware, that software does not belong to the physical world. It has a different nature, right?
It has the nature of like the space in which a topology is embedded. It has the nature of space. It's not a thing.
So ontologically, it's not a part of the physical thing. It comes from some other place. It has a different
ontology
nature.
Doesn't include a physical thing as a separate thing.
I'm not really sure I follow. Please explain.
Okay, I'll repeat it. My ontology doesn't see a physical thing as a separate
So
thing
you only
that
have
can be
you only have one kind of objects in your ontology?
One kind of process.
So ontology is I'm failing to follow. Ontology is not about processes. Ontology is about the nature of things. So I'm kind of classifying.
What I'm saying is the nature of things is a process. Things are part of a process. So what exists is a process.
But then I'm failing to understand the word process, because in my mind a process is something that happens with already existing objects.
Sure.
I cannot imagine a process without.
Yes, that may be how you think of it.
And
that's a good pointer to what I'm saying. But I'm saying that basically what I'm saying is there is only process. There is only process. And then if you look at it in a certain way, you can see the things that are, say, the result of past processes or are transforming right now. And then you have the process itself and the energy to drive the process. Those three things are inseparable. And that's all there is.
Okay. I think we're going to have to dive in on your ontology one day. I've never heard such a view before.
Well, something to think about is like, is a field within physics material? And probably help make sense of what was just said, right? There's a lot of to a field within physics, but is it real, or is it just a concept that helps explain our explanations or our observations?
That's exactly the kind of question we are asking, but I'm not even getting to the physics yet. So we're only asking about numbers. The same exact question you're asking, I'm only asking about numbers. Very simple. Is the number 1 real? Does it come from the real world? Does it come from my intuition, so my reflection? Or does it come from some other perfection that I cannot access? All three of these answers have failed. So there's a separation between me, my inner dynamics, and you can call it fake, you can call it real, but this is the history of philosophy. That's how it happens. We had dualism, running around. You can be not a dualist, and we will discover other views in a minute. So there's my inner dynamics, and I'm reflecting in my mind, and then I go out to the world. So this kind of a rationally intuitive based version doesn't cut it. The other part, which is the physical world, so that's another part of reality, doesn't cut it. And imagining a third reality above us and then having it dictated doesn't really cut it as well. So probably I am Shumais. I'm not even sure how to pronounce your name, sir. I'm sorry. I am Shumais.
You can just call me Adam.
Adam, okay, yeah, that works. Adam is a lot easier. So Adam, maybe the following view is a bit more to your liking. Okay, let's just talk about that fourth view that kind of tries to solve this problem in a different kind of way than positing a source.
Perfect.
That fourth view.
You're a great teacher. You prompted us for a prediction, and now you're going to give us a new response. Very good. Thank you. You
You're
have my
more
full
than
attention.
welcome, sir. Thank you very much. I'm really happy that people are enjoying this. That's exactly what I want to hear. Thank you. So that fourth theory is called formalism. Again, all of these theories were kind of interacting, right? And especially that realism and formalism here, they're kind of developing kind of in the same period. Formalism a little bit later. Mathematics, they say, is a system of formal rules and symbols. Nothing more, nothing less. And the formalist view, the only requirement, the minimal requirement for a formal system, for a mathematical system that produces all that higher mathematics and all the infinities, the only requirement is just consistency. And how do we define consistency? This is how we define consistency. Consistency means you can either prove this, or you can prove, if you're following on the Jitsi, it's negation. That's consistency. Either this is the case, or this is the case. Done. That is the only requirement. Can you find a proof for phi or p or whatever? Yes, okay, that's it. Can you not find a proof? Okay, then we don't know. Can you find a proof of the negation, or that the negation creates a contradiction? Done. That's it. That's all we want. Its meaning, its reflection on the world, its relationship with objects, that's not our business as mathematicians. If the physicists have found some applications for some of the things that we have, that's their business. And we will talk about science some other time in the future. How is it that science has used mathematics to explain the real world? But most of the mathematics hasn't been used to do physics, in which case, what is it? It's meaningless. Oof, that's a totally different line from all the other three views we've just seen. All the other three views, they maintain that mathematics has a relationship with the external world somewhere. The formalists, drop it. Drop it completely. We don't even care if we make sense to the meaning of the world. Nobody has ever asked where chess comes from. Everybody plays chess. Nobody ever asked where football comes from. Everybody plays football. Why should we ask why mathematics has come from somewhere? Or where has it come from? Or what's it? It's just a game. There are rules. You cannot write this in mathematics. So if you follow me, 1, 1, 1 plus plus equal 3. You cannot write this. This is illegal. What you have to write is 1 plus 1 plus 1 equals 3 in that order. And that is a legal move. Just like in chess, you cannot move the pawn 3 spaces. Just illegal. Some of us are better than others at this game. We call them mathematicians. Some of us are better than others at the game. We call them footballers or Formula One drivers or chess players or grandmasters, right? Doesn't have to mean anything, just a game. Doesn't have to reflect on the real world with anything. It's just a formal system with some rules that we've invented and we're playing and messing around with it. The physicists have applied it to the real world. Ask them. Okay? It's their problem why some of our mathematics is working. And again, I'm leaving that question open because there is an answer. But then we're going to go into the scientific theory, and I'm only talking about mathematics here. I'm limiting myself here. So this formalist school just says, give up on the meaning entirely. We are only following formal rules, and that's it. This is what mathematics is about. Period. They gave up on the search altogether. Kind of cheating. You know, when we were discussing the origin of this, we're kind of cheating. They kind of gave up. But then, if neither this world or our inner dynamics or a different universe can answer, well, there's a problem with the question then. That's kind of the formalist attitude. If your question, we've been looking for answers for your question for over 2,000 years now, and we still haven't found an answer, probably there's something wrong with the question. It's kind of begging itself. It's a begging the question fallacy. You're asking what is the meaning of mathematics and where does it come from? And we're telling you, when you ask that, you're going to go down a rabbit hole that never has an answer. It's a rabbit hole that is doomed to fail. Well, don't go there. Don't ask the question. If you really want to know how mathematics developed, it's a historian's job. Oh yes, René Descartes was sitting in his bedroom and he thought of, he was late in the morning. By the way, this is a real story. Huh? This is what he writes. The way he came up with the Cartesian frame, this XY frame that we all use. So he was late in the morning. He liked to sleep late. And one morning, the sun was shining through his window. And you know these old windows that they used to have, where they have a wooden framework in the middle that was like the shape of a cross. So the sun was shining through the window, and it casted the cross on the wall. And there was a fruit fly flying around the room, and then it landed on the wall, and it was moving around. And Descartes was watching it, and all of a sudden he's like, I got it. If I draw this system, or he called it the frame. Why do we call it frame? Because it was a window frame, right? So if I draw this, then I can divide the wall into 4 different pieces, and now I can say, oh, the fruit fly is in piece number 1, piece number 2, piece number 3, piece number 4. And now if I put numbers on these things, I can know exactly where it is. And that's how he claims in his journals that he got the idea. Now, a realist would look and say, of course, he got the inspiration from the real world, of course. A Platonist would say, oh, the cross that he saw, it was an instantiation of some perfect cross up there, and then he got the idea. And then intuitionists would say, oh no, it's somewhere in his intuition. He kind of thought about it and says, this makes so much sense, this is so good. And it was the source of that result was his inner intuition that this makes so much sense and makes it easier. Well, the formalist would look at them and say, I don't care where he came up with that idea. I don't care if it even works. All I care about, is it consistent? Does it have some rules? Does it have some things that are not allowed? So some forbidden moves. Do everybody know the rules? Can we follow it? Yes, done. That search of how we came up with it and why we came up with it and so on and so forth, that search is irrelevant to the mathematician. It's a purely historical thing. If we know it or we don't know it, it doesn't really touch the mathematics. If we know that this math applies to the real world or no, it doesn't touch the mathematics. It touches physics. It touches the historian. It doesn't touch the pure domain of the mathematical theories. This is what the formalist school says. Your questions and your impressions about this.
Can you give, I'm sorry, I'm not able to look at the slides right now, but what are the dates of the sort of founding fathers of formalism, so to speak?
Okay. I'm going to speak very generally here because I don't have the actual dates in front of me, but I can tell you names of people, and those people have lived in sort of an era. So those formalists, people like Tarski, they have lived in the beginning of the 20th century. People like David Hilbert is also a formalist. people like, who else is a formalist?
Kurt Gödel.
Sorry?
Kurt Gödel.
Gödel is a Platonist, actually. There's a whole version of Platonism.
Oh, I see. So he discovered his incompleteness as an argument against formalism then.
Yeah, you could interpret it in that way. Yeah, definitely. Kurt Gödel was a Platonist, and he kind of developed that view. I'm not talking about his view here today, but he was more a Platonist than a formalist. David Hilbert famously was a formalist as well. He tried to kind of develop those rules of arithmetic in a certain formal way, following the example of Russell. Russell was not, he was kind of a Platonist somewhere when he did that, belongs to one thingy. Hilbert, because he was a student, he kind of tried to get rid of all that influence. And he did a lot of work on piano arithmetic. We are talking on the verge of the 20th century. So all these views were kind of competing during the same time between realism. Realism was a bit earlier, so we're talking, let's say, 1850s or 1840s, somewhere there. And between Intuitionism and Formalism, the debate raged in the beginning of the 20th century, onto, continuing towards our day, This debate we still have Platonists today among us. It's not like the view is not popular anymore, but kind of declined after, 2,000 years of Plato. Yeah.
May I ask, how would you what is your opinion?
Oh, I'm getting there.
About how you would categorize Cantor, because he was
sorry,
around
I thought you
doing
were
some
my
really
opinion on
interesting
the
stuff.
issue. Okay, Cantor.
No,
Yeah.
on Cantor. Which camp would you say he fell into, or was he a hybrid?
I'm not sure, actually. I'm not really sure, because Cantor, the thing about these things is you have to read the actual person and not about him. And I've never read Cantor himself. I read people writing about him.
I've read translations. He wrote in German.
Yeah, and what do you make of it? My impression is somewhere near the school of logicism, which is a school that lives. That's the thing. Russell was a logicist as well, but he has some Platonist in him.
Okay.
Again, we have to be very careful about these things, because nobody said I'm a Platonist openly. Nobody said, oh, I'm a formalist openly. Nobody, you know what I mean? Like
right.
we
It's
kind
only
of
in retrospect that we had a name for it, and we could point.
Right.
We can say
it wasn't even a thing back then. So
right.
I have to get back to you on Cantor on this one.
Yeah,
I have
sure.
to get back to you.
Most likely, they would probably show a confusion amongst the three philosophies, because some of the important questions that they were raising hadn't been settled until after their careers.
Oh, they haven't been settled, some of them, until today.
Oh, sure, yeah,
and,
for sure. But the only thing I'd say about Cantor is in relationship, since Hilbert loved him and Kronecker hated him. I don't know if you know the story
no,
of
not
Kronecker.
really, not really.
Kronecker was Cantor's thesis advisor, and then he went on to be his greatest enemy, like trying to get him fired from all his jobs and stuff. He tortured him, and he tried not to get his
the
work
infinity
published.
thingy, because of that proof.
Yes.
Oh wow.
Yeah.
Okay.
So I would count Cantor. Hilbert famously said, "We must live in the paradise that Cantor has created for us." So I would say that a lot of his ideas are supportive of sort of a Platonist view, but I think it was his view of infinity. He basically, my guess is he equated infinity with God. And so by trying to prove that infinity has to exist, he was trying to show that some kind of absolute infinity must be present, and we can prove it mathematically.
So Wissam here agrees with you. He says he's a Platonist, and that he was committed to infinities. He rejected pure formalism and constructivism. Okay, cool. Thank you, Wissam, for the information. So it appears that Cantor was a Platonist. So he believed that actually what that quote unquote paradise he created, it appears that he actually believed that these are actual objects, or they are the influence of that modern formalism thing, where sharing that view with what's his name, Russell.
Yes,
I will get back to you on this one. I'll get back to you.
Yeah. It's an interesting question, because a lot of people nowadays, especially if they're not trained in mathematics or philosophy, have no idea that it's very difficult to think like Cantor would think, because Cantor was a deeply religious individual out to set his life to prove that God existed mathematically. It's hard to imagine what the world looks like from that view completely, right? We just have to speculate in retrospect and see how the currents of these ideas flowed through culture. It's really
Yeah.
interesting that these issues are not resolved, even though I think quantum mechanics and other fields of physics have promised that they would resolve them once and for all.
Yeah, that's a good point that you're mentioning, and I should mention also that during that period we had the First World War, the Second World War, and then the heated part of the Cold War. So all of these events I'm describing are, either before the World War I immediately, let's say by 20 or 30 years, or during that period or afterwards. And so there was a lot of political influence as well. So American sort of scientists had a certain inclination. Europeans, let's say from one camp or another, the Germans had it. You know what I mean? Like there's a lot of, and then the Germans who left Europe and then went to the States kind of developed a certain other characterization. There's a lot of politics and culture that also lives in this. It's not purely, talking about mathematics as well. There's kind of this this inner drive that we have inside us to kind of distinguish ourselves, etc., etc. I can never, discount that as a probable source for the for this for these heated debates, as you say, between, let's say, Kronecker and Cantor. There's some religious, perhaps, because Cantor was also, I think, Jewish. So probably there's some influence of some deism, let's say, over there. Again, I don't know. I'm relying on Wissam here because I haven't read Cantor's commentaries himself here. We have to be very careful before we give guys these symbols. All right.
Well, if you like philosophy of mathematics, I know you want to get on with your presentation.
Oh, I just have one more slide. That's it. Yeah.
The next, I would highly recommend you go track down the papers that Cantor wrote at the foundations of set theory.
Oh yes. Absolutely. We will see that the answer for that. There's there.
Fascinating. Yeah.
Yeah, absolutely. Yeah, absolutely. It should be there somewhere. If not explicitly, it should be lurking there 100%. So this is formalism, guys. They just say, well, you know what, forget about it. We're not concerned. This has no impact on mathematics whatsoever, whether it has an application or not, whether it has an origin in the physical universe or our intuition or whatever or not. It has zero impact on the world. It has zero impact on its own merit, and its merit comes from consistency. That is their claim. The problem is that, well, okay, we gave up on meaning. So we are on slide 16 now, nearing the end. We gave up on meaning. So it solves kind of the origin problem. It doesn't really solve it. It just says it's irrelevant. It's a question of, extra information. It doesn't really hurt or benefit. So the question one, or where does it come from? What, it kind of, okay, they gave up on it. Fine, we're going to give it to them. But there's another question that was not answered, which is, what is it ontologically? What is this 1 + 1 = 2 referring to? What is the meaning of all of this? Okay, you say there is no meaning. Okay, fine, I give up. I'm sorry, I used the word meaning. I'm sorry, you say it's meaningless. Okay, what is it? What is the nature? This object one, is it somewhere in the real world? Is it somewhere in the formal, what is it, the world of forms? Is it, what is this object that you're dealing with? It's consistent, fine, okay, what do you mean by, like, where is that consistency thing? It's just an idea that you have in your brain? What are we talking about, really? And the final school I want to present, which is kind of my position, I earned the right after explaining the previous four. It starts with this question. So it's a let's say remark that without really knowing these answers, we can still do mathematics very successfully. So number one. Number two, we cannot really do mathematics without a physical representation of that mathematics. Again, no one has ever failed to do mathematics because we don't know where it comes from or what the meaning is. So the formalist kind of has a point. But then we cannot really do mathematics without a physical representation of that mathematics, either as a bulletin board or as a blackboard or as a paper or as a computer, or even if you do math in your head, then you are kind of either imagining one of those objects in your head, which is what people have, so they imagine something clicking or something rotating or some numbers moving or something, or if you have none of that completely. And we're going to go back here to the example that was mentioned in the room about, I think, Jonathan, were you discussing how dogs do it in their brains, etc. So that form of calculation, what do we say about that? Well, that's also a physical form, tacitly there, right? But it's there. It's kind of a neural network that is built in. Again, I'm stepping into Wissam's territory here. It's kind of built in those beings and animals and all that stuff. So how does there's this fascinating animal, the archer fish. Have you seen an archer fish? I should have put a video here, but I was, I thought it's not worth it. There's this fish that is from underwater. It kind of squeezes water to snipe insects that are close to the water, let's say on a very close leaf to the water. So it kind of collects the water, presses it with some muscle, and then shoots. The problem with that is, we know that light bends, it refracts when you cross from water to air and from air to water. And so that archer fish is not only doing the necessary calculation to fire so it's not only doing regular projectile calculation tacitly in its neural network. It's actually doing a much more complicated task, because it has to calculate for the bend of the actual image that it's seeing. It cannot shoot where it sees, because the object is not where it sees. It will be somewhere. And of course, you can ask why it happened, and then we can talk about evolution and all that stuff. But what concerns me is that this piece of knowledge, it's there in that neural network. So I cannot think of any piece of mathematics, abstract or concrete or one object or infinity or whatever, that does not have some physical representation somewhere with us. Infinity has a symbol, functions have symbols, they have proofs, and they have whatever you're doing, you're writing a proof. Is it on a piece of paper? Is it on a computer? Is it on a board? In what way are you coding that information? There must be some physical representation for that coding, either as somewhere in your brain, in your imagination, in your memory, or somewhere out there in the world. Which leads me to physico-formalism. It's a formalism that says mathematics has nothing to do with the physical world. It has no meaning in the physical world. However, the objects of mathematics are exactly physical objects and only physical objects. The physico-formalist thesis was laid by Laszlo Szabó of LT University, retired now. He is my professor, and I shamelessly follow him. He says, the logical and mathematical facts, being formal facts, are nothing but physical facts of physically existing formal systems consisting of signs and derivation patterns embodying in concrete physical objects. What is mathematics? Mathematics is this body that we are writing on the piece of paper. Premise 1, premise 2, premise 3, theorem 1, theorem 2, axiom 1, axiom 2. This is the mathematics we're talking about. That's it. We have answered the nature. So what is it really? It's a physical system built in with physics, whatever those physics are. What does it mean? It means nothing until it gets applied somewhere in the physics, which we will not discuss the details of today, but we will leave it for another time. So how is that application happening is a different question. We're just asking about the mathematics now. That mathematics is not hurt or benefited, whether it's applied in physics in the real world or not. That mathematics exists as a formal system. So here there is consistency and dedication. So this is consistent. So they absolutely right, those formalists to deny any connection, with the physical world, or any other world for that matter. So consistency is really what defines that system. But what is it ontologically? To answer that second question, or the first question we asked, it is a physical entity. And that physical entity exists on our hardwares, on our brains, and on our bulletin boards. And this is my position. Yes, mics, questions, discussions. We have finished, by the way. These are the only 5 schools I will present today. These are the main 5s, the main 4 actually. The 5th one is a new development. I will lead you at the end of the discussion to where you can find more and more. But I would like to hear your opinion, at least, about the formalism and the other version of it, which is the development physical formalism.
So Shamash, in the first session of this course, in a discussion that we were having about my particular form of Platonism as I was understanding it, you indicated that there was a 5th form of perspective, a 5th perspective that you had learned from your thesis advisor. Is that correct? Is this what you're talking about?
It's the one I just it's the one I just explained, the 5th one.
Yeah, great. So I want to ride a hobby horse that I've been building until it turns into sawdust, and I'm aware that I may be a hammer in search of a nail here, but I want to revert back to the perspective I was coming from, that the fact that other species besides humans engage in behaviors that is demonstrably in congruence with our formally developed math, be it, the example I keep coming back to of the dog doing essentially calculus, or amoebas solving computational problems in working through mazes, or the archer fish that you're talking about. I would propose, I hesitate to use this phrase, but I would propose that perhaps a suitable answer, which may be consistent with one of these 5 positions, I haven't thought it all the way through, but a suitable perspective may be obtained by thinking about to what degree does acting in accordance with maths ensure continued existence in the physical world. So I hesitate to use the word Darwinist perspective, but the fact that species or individuals of species that act in accordance with what we know to be formally provable mathematics have a higher survival rate than those individuals which make flawed calculations or use a flawed version of a math system. At the very beginning, I kind of flippantly wrote 1 + 1 = 2 for sufficiently large values of 1. But if, for example, I'm a foraging animal and I need to make a decision about whether this is a whole apple, or, a third of an apple, or 1/10 of an apple, as opposed to a whole apple, my decision about whether to forage that particular object in the world, as opposed to picking one that actually does equal 1 and foraging twice and getting 2 apples, as opposed to getting 2 times a lesser value of 1, a third of an apple, and ending up with 2/3 of an apple, I would have less success continuing to exist in the ontologically verifiable world. So this again doubles back to the thing I was walking around of, and one of the other participants in the group was talking about, of it being a software hardware kind of thing, that the math is an interaction of an actor and the ontologically verifiable world. So I don't know if any of that, if that made sense, if it was internally consistent, but I just wanted to throw it out there.
Yeah. Okay. So if you're following me on the Jitsi, I kind of made some freehand summary of what you're talking about. Probably if just trying to make sure that I get your view correctly.
Okay. I'll try to get to the Jitsi.
Yeah. It's fine. It's fine. I'm gonna do my best actually to read it if you can. So I think the summary of the question is, to what degree that be aligning with mathematics guarantees your survival. And you gave the example of an animal understanding, let's say, arithmetic by understanding, quote unquote, right, that if it eats, let's say, 2 apples, it's better than eating 1 apple, or let's say a third of an apple, or something.
The general point I'm trying to get to as a conclusion is that the empirical proof that math works, for lack of more precise terms, is the continued existence of organisms that act in correspondence with the math that we have discovered to have existed, that there's a correspondence out there.
Okay, I understand you. I understand you now. Now I know I understand you 100%. So very quickly, because I don't think I will be able to answer your question fully, because we're not talking about the physical theory here and how do we make it. Okay, but just very quickly, not to leave you hanging. So those mathematical theories that you posit are kind of participating in our likelihood of survival. You're absolutely right. Yes, of course. Knowing the mathematics helps you survive better. But what mathematics are we talking about? Is it all the mathematics, or is it a small part of the mathematics which finds its way as a translation of whatever, or let's say a reflection, or let's say a model, whichever one you prefer, right, with different ontological weights of the real world? It's those mathematics that we are talking about. We are not talking about topology. We are not talking about hyperbolic geometry. We're talking about that small portion of the mathematics that we use as human beings. Forget about the animals, which we call physics, right? Which we use, at least, let me not make that jump, which we use in physics. So we have looked at the physical universe. We have created a certain theory about it. We tested that theory. We improved that theory. We put an equation to that theory to make it much more precise and much more measurable and much more reliable. And then after this, all trial and error, we have this knowledge now. Now, whether this has been done knowingly or consciously, or let's say tacitly through evolution, is not my point. My point is we have been able to do this as forms of life. And it is that part of the mathematics that participates in our survival. Knowing stuff about infinities has nothing to do with our survival whatsoever. In fact, as human beings, we had no idea how to deal with these objects until very recently. We did not even conceive of them. When what's his name? When Leibniz was writing, with the beginnings of his calculus, or Newton, they were kind of afraid of this new being, which we call the infinitesimal. They kind of used it, and then later people, they kind of deny it, like they've banned it, like it doesn't make sense, and there was a huge debate. Now it's just given for us, right? And before then, did we not survive? Of course we did. We're now surviving better because of this new model that we have. But it doesn't mean that the model itself has anything intrinsic in it. The calculus itself has nothing to do with it. The calculus applied to the physical theory, used in the physical theory, has the benefit. And what is the physical theory? The essential thing in the physical theory is it is built with interaction with the world by trial and error. At least that's my position now. I'm jumping ahead in the series, but it has nothing to do with the mathematics itself, if that makes sense. All these episodes are posted on the Scientific Discourse channel and my own personal channel. You can find them on the last slide. I have them on the Jitsi now posited. You can join our house and listen to the replays, and if you want to listen to them with the slides, edited without the pauses and the awkward technical problems, then I will have that on my YouTube channel as fast as I can edit it and upload it. Also, please subscribe to the Scientific Discourse YouTube, where all these lectures, mine and John's and Sam's and Ben's and all those nice discussions are regularly uploaded. Just look for Scientific Discourse on YouTube, or write the name Philosophy Wednesdays, and you will find it easily. I will put a link in chat when I have the chance. So we did 5 schools today. The first one was Platonism, which posits that mathematics come from some perfect universe that is reflected onto ours. We did Intuitionism, which posits that Mathematics come from somewhere in our intuition, in our minds, and this is how we know that it makes sense, and this is how we know that the proof is fine. We explained also realism, which entails, or which kind of explains mathematics by its relation with the real world. So something along the lines of what Sis Jane and Jonathan were kind of revolving around. We also explained formalism, which rejects the entire body of the entire search, the entire endeavor of looking for where it comes from. It kind of keeps it away from mathematics and looks for explaining mathematics just by its basic principle, which is consistency for them. So those are the four schools. If you want me to comment on each one of them, or if you want to ask a question about any of it, please shoot.
So you were referring to, I think you were referring to math, but you cited 4 worldviews. I think one was
four
Platonism.
main schools. I can actually probably take a pause in a minute and then name other schools that we haven't mentioned.
No, I know. I think the last one you said was formalism. Is that what you said?
The very last one, number 5, was kind of a modification on formalism. But
you said 4 before. Yeah, formalism, right?
There was 4 main ones, and then there's the 5th one that kind of developed by like my advisor, and then we're kind of working on it still. But yes, there's kind of four main schools: Platonism, Intuitionism, Realism, and Formalism. Yes.
What do you, if you don't mind, what do you think of conceptualism?
Wissam has written in chat an explanation or a summary of both positions. Let me read it very quickly. And again, thank you very much, Wissam. Highly appreciated. Intuitionism and conceptualism differ in focus and scope. Intuitionism is a philosophy of mathematics emphasizing the mental construction of mathematical objects, rejecting classical logic, the principle of excluded middle, etc., and viewing mathematics as a dynamic process, which is what we explained. Conceptualism, by contrast, is a broader ontological view, holding that universals and abstract entities exist as mental constructs, not as independently real objects, while accepting classical logic. So they kind of made a broader. You're not liking it.
No, I love it. I love it. Sorry.
That was for loving. Okay, people usually use that.
No, it's like It's like it's to say yes when you define conceptualism.
Heck yeah. Okay,
because I fall in line with what he says, or whoever wrote that, he or she, whoever said that. Thank you.
So absolutely, thank you, Wissam. Okay. If there's no other business, I will refer you to slide, what is it, 17, 18, 19, where there are more links for you to find out about this topic if you have a hunger for more. There's the Stanford Encyclopedia. They have a very nice entry there. Britannica has a nice entry about philosophy of math. They're all linked in the slides over there. If you just go to the slides, you will find them. Wikipedia has a nice entry, nice-ish, no problem with that. And I will refer you to a YouTube video for Ray Monk. Ray Monk is not per se a philosopher. He started as a biographer. He wrote biographies of Bertrand Russell. I think he wrote also the biography of, what's his name, Oppenheimer. And I think some of it, at least, or if not the entire thing, was used to do the movie. So Ray Monk is well known, and he is Professor Emeritus, and he was lecturing about philosophy for quite a long time. So he has a very nice classic lecture on the philosophy of mathematics, 35 minutes, but very dense. And a little bit more technical than what we have had here. I tried to remove all the jargon as much as I could from the presentation today. But if you feel the hunger for more, and you're up for the more technical stuff, the Ray Monk presentation or lecture is a classic initiation for anybody who wants to find out more about the nature of mathematics. We have reached that point in the room where I thank you all for being here, especially the people who have participated. Aaron, Jonathan, John, you just arrived, but thank you for coming, dude. Wissam, of course, all the others, thank you so much for being here. And again, the Scientific Discourse house will have this presentation. And if you just find it on YouTube, I will put a link in the chat right now. If you want to watch this again with the slides, or if you want to refer it to someone, please do so. Highly appreciated. If you feel hunger for more, or if you've missed the previous episodes, please do so. And if you have friends that you know are interested in this, please let them know about the channel and about our club, either the Scientific Discourse one or today. We open rooms every Wednesday in Philosophy Wednesdays at 17:30 GMT. That is exactly, my God, 3 hours ago. And at the same time, on Fridays, we have the Scientific Discourse houses with Professor John Mallinckrodt, who is with us today. Give him a follow. His rooms also are so enriching and just so good. John is way better than I am. John, do you know what is about? What's Friday about?
You know, I'm sitting here thinking, boy, if I'm going to do Friday, I got to get that together today. I had a couple of ideas.
Okay, never mind. Nobody heard you. Nobody.
Yeah, so I don't know. It may be an open discussion because tomorrow's Thanksgiving and
Nobody,
all that stuff.
nobody heard you. Nobody, the professional Scientific Discourse people. Okay, thank you very much for being here. I will play you guys out. I appreciate you so much. See you guys next week, same time, same place. Scientific Discourse or Philosophy Wednesdays. Adios.